Hi, this video is about problem solving, kinematics, just instead of a basic one object, one phase problem, this is now a two-phase problem. So there are two steps to this one because there are two different accelerations. So the problem we've got, a bowling ball is dropped into Lake Menomin from the bridge 5 meters above the water. So after hitting the water, so it's going to go through, hit the water, then it sinks to the bottom with a constant velocity equal to what it hit the water with. The ball reaches the bottom 1.5 seconds after it is released. What is the depth of the lake? How deep is the lake? All right, so this is a two-phase problem. So it's a two-parter. And we're just going to use the same process that we've been using for everything. That's what we do, is we use our problem-solving process. We're just going to start with a picture. So we've got the picture of, and then there's the base. So we drop a bowling ball from here. It's going to hit the water going some speed, and then it's going to fall down and hit the bottom of the lake. And sure, I can put a little person in. There we go. Okay, and we want to know, what is this depth? All right, what should I pick as my origin? I see three possible places that would make sense physically. I could have this be the origin here where I drop it. I could have the water surface, the surface of the water be the origin, or I could have the bottom of the lake be the origin. All three work. You will get the same answer no matter which origin you choose. Sometimes it's a little easier if you pick one. Sometimes it's just like, oh, I got a couple negatives here, you had a couple positives. It's okay. So you can pick whatever one you want. For mine, I'm going to choose, let's see, what did I choose for this one? Okay, for my answer solution, I chose this as my 0. Again, pick a different one if you want. You can still follow the steps, and you'll just have some negatives. You might have a 5 where I have a 0, whatever. Okay, so we've got my origin. I'm going to do my standard coordinate system. Up and right is positive. And now we're ready to figure out what we know. So let's do our chart of kinematics variables. X initial, X final, V initial, V final, acceleration, and time. All right. Do we know X initial? Do we know where it starts? I chose this as my origin. And the problem stated we are dropping the ball from 5 meters above the surface of the lake. So this is 5 meters. So we do know our initial position, 5 meters. X final, do we know where it ends? And now here we have to start saying, ah, man, well, yeah, this is X final, but because my acceleration here is different than my acceleration here, I have to do this in 2 steps, because if you think about our chart, there's only one place for acceleration. When we're solving problems, we have to solve it with one constant acceleration. So I'm going to do this while we're in the air. Okay, so we'll do this from here to here, which means I do know X final, it's 0. Initial velocity, so that's right here, and in this case it's dropped, so we got nothing going on there. Final velocity, do I know how fast it's going when it hits the water? Nope. Okay, so that's a blank. Do I know what is the acceleration? Well, yes, it's in free fall, it's falling and accelerating due to gravity. So I'm going to use 9.8 meters per second squared. And in my coordinate system, that's a negative. The time, do I know anything about the time it takes? Nope. Okay, so that's the first part. Now let's do part 2. So this is part 2 from here. I guess this is right here to here. That's my initial for part 2, that's my final. All right, X initial, X final, V initial, V final, A and T. Acceleration, oh, I was about to put gravity in. No, it's not. Okay, let's go through. X initial, well, I set that to be 0. X final, how far is it down below? Well, that's what we're looking for. That's really my target variable, so I'm going to put my question mark there. V initial, do I know how fast it was going when it hit the water? Nope. V final, nope. Acceleration, I do know my acceleration. The problem stated that in the water it moves with a constant velocity equal to whatever it hit the water with. Constant velocity means no acceleration, 0. Do I know how much time it takes to go here? Nope. So I don't know time. Oh man, all I know is that these two are going to be the same because I have no acceleration. And that's what I'm looking for. All right, that's what I know. This is a two-phase problem. What can we do here? So you always start with your target variable. What are we looking for? In this case, I'm looking for the final position in the water. How can I solve for that? What equations do we have available that might get us x final? All right, the long equation. Can we do that? X final equals x initial plus v initial t plus 1/2 at squared. Okay. X initial is 0. This is what I'm looking for. V initial, don't know. T, don't know. Well, that whole term is 0. Not very helpful. Great. V final equals V initial plus AT. Doesn't have what I need in it. Let's hope the third one gets us something. V final squared equals V initial squared plus 2, acceleration, change in position. V final, don't know that, acceleration is 0. Ah, look, V final equals V initial. We knew that, there's no acceleration. So, you stop and you say, I don't know enough. But we do. We know two pieces of information that connect these two parts. We know that the speed of the bowling ball in the water is equal to how fast it hit the water with. So this velocity, the final velocity here, when it hits the water, is going to be equal to the initial velocity in the water, and also the final velocity. So that's one of the pieces we know. So maybe if we can figure out what that is, we can get somewhere. The other piece that we were given is that it takes 1.5 seconds. The ball reaches the bottom 1.5 seconds after it's released. So can I put that here or both of them? Think it through. Make a guess. Here, both, neither. Where does that 1.5 seconds go? If you think it through, hopefully you get neither. This is the time for here plus here. It was the total time to go from the drop all the way to hitting the bottom. So that's not the time in air, that's not the time in water, it's the combination of the two. So we have time in water, and we've got, oh, nope, that's air. Oh shoot, time in air, and we've got time in water. And now we have another equation which we know to be time in air plus time water equals 1.5 seconds. So hopefully now we'll have something to work with. Hopefully. Okay. What I'm going to suggest is that since we really don't have any information on this side, is that we see if we can figure out something over here. And we know that we can drop this over to this side. So can we figure out the final velocity in air? Well, let's look at my three equations here. X final, yep. X initial, yep. V initial, yep. T, don't know T. 1/2 A, okay, we don't know T. V final, that's what I'm looking for. V initial, yep. A, yep, don't know T. Dang it. V final, that's what I'm looking for. V initial, yep. 2, A, yep, we know A, and we know the change in position. Got it. So let's use this equation to see if what our speed is, our velocity is when it hits the water. So that bottom one. Okay, and now I gotta be careful. My acceleration isn't 0 anymore. Alright, rewriting. V final squared equals V initial squared plus 2 times A times the change in position. This is what I'm looking for. V initial is 0. That drops out. 2, we know A, and do we know the change in position? Yeah. And remember that anytime you see a delta, it's final minus initial. It's alphabetical. F comes before I. X final minus X initial. Alright, so V final squared equals 2 times my acceleration, 9.8 negative, and X final is 0 minus X initial, 5. 0 minus 5, ooh, I'm a little concerned because this is a square and I got a negative. But we're going to be okay. Can you see why? I got a negative here. I got another negative here. We're going to be okay. So v final squared is, let's see, it's going to be about 2 times 5 is 10, about 100. If we do the math, what do we get for v final? We get 9.9 meters per second. Oh, well, that's not the squared piece. V final is 9.9 meters per second. So yeah, v final squared was about 100. V final should be about 10. But we took a square root. When we take a square root, we have to stop and say, I have 2 roots. This could be a positive 9.9 or a negative 9.9. Given my situation, given the physical situation, what makes sense here? Well, my final velocity, when it's about to hit the water, is going downwards. I choose the negative root. So my final velocity is negative 9.9 meters per second. That's pretty fast. 10 meters per second is what? 10 times a little 2 and a bit. It's like 22 miles an hour. So that's going pretty fast. Do we know anything else that might tell us if we're making sense with the numbers? Not really. 5 meters, that's about 15 feet, 16 feet. So how fast is going after 16 feet? It would be going pretty fast, actually. All right, so plop that in here. We now know v final is negative 9.9 meters per second. So now we know our initial velocity for part 2 and our final velocity for part 2 are both negative 9.9 meters per second. Can we figure out x final now? And I erased my equations. Okay, so we want x final. Can we use this one? V final we know, v initial we know, 2, we know the acceleration, we know delta x. We could use this one, but all that's going to tell you is 9.9 equals 9.9. Not very useful. How about, what are the others? X final equals x initial plus v initial t plus 1/2 at squared. Okay, I'm looking for x final, that's what I want. I know x initial, I know v initial, don't know time. And yeah, that would be 0. So if I had time, I could use this one. The third equation is v final equals v initial plus at. Well, it doesn't have x final in it, so that's not going to be helpful. Again, we stop, we say, we don't have enough information. But we haven't used that last piece. This one right here. We haven't used the fact that we know that the total time is 1.5 seconds. If we could figure out what the time in air is, we could figure out what the time in water is, and if we know what the time in water is, we can use this equation. So we could use the long one. So let's give it a try. Now, what I'm going to try to find is, what is the time in air? Because once I know that, then I can get this, and then I can use this equation to get the thing I'm trying to get to. Okay, let's do some erasing. Time. All right, so we need to figure out the time it takes to fall 5 meters from being dropped. If you look at our 3 equations, we've got v final equals v initial plus at. We could use that one. We could use x final equals x initial plus v initial t plus 1/2 at squared. So we've got 2 equations that would get it to us. The third equation doesn't have time. Not going to worry about that. So what I'd like you to do is, I would like you to do one of these 2, okay? So either use the long equation, there we go, or use v final equals v initial plus at. Use one of those and figure out what the time is. Hit pause. I'll be here when you get back. Okay, so if I'm trying to find the time, I look at these 2 and I say, well, that looks a lot easier to deal with, this equation does. So let's see if this would actually help us. We know v final, right? Yep. We know v initial, we know acceleration, and we know time. Okay, so v final, I'm looking for time. V final, I'm going to subtract v initial over. equals AT, so my time is going to be V final minus V initial over my acceleration. V final, negative 9.9. V initial, minus 0, over acceleration, negative 9.8. Negatives will cancel each other out, and I can say that's pretty darn close to 1. I think it ends up being, 1.01 seconds. Just use 1, that's fine. So what is this? This is the time in air. So this is the time it takes in air to drop from the bridge to the surface of the water. We know the total time it takes from it to go from all the way up here to the bottom is 1.5 seconds, which means the time in water, 1.5 minus 1 is 0.5 seconds. Now I'd really recommend you do the other equation too and see if you get the same thing. The only thing you have to watch out for is that you've got a t squared in there, so you're going to take a square root. You'll get positive and negative. If we're dealing with time, we're going to choose the positive time. So give that a try while I'm erasing. All right, we're at our last step. Now we can actually solve for the thing we're trying to figure out, which is how deep is the water. So we're looking for x final here. And we have no acceleration, so which equation would be good? Well, we have two equations that have position in them. Will the long one work for us? Let's give this one a try. The initial t plus 1/2 at squared. X final is what I'm looking for. I know x initial, it's 0. V initial, I know. I now know my time. Woohoo! 1/2 a is 0, so this whole term drops out to 0. X final equals V initial t. Doesn't that look easy? Yeah, that last step is actually nice and easy. It's a great relief after all that other work. So let's solve it. X final is V initial, negative 9.9. Okay. Times our time, 0.5. And, if you do this, you're going to get a negative, what are you going to get? Negative 4.8. You can do 4.85 if you want. Now negative, we have a negative times a positive, so that's a negative. Does this make sense? And again, never just stop with an answer. Always stop and say, does it make sense? Does a negative sign make sense here? Well, I chose my origin to be at x equals 0. And in this case, I end up below my origin, so yeah, I end up in a negative position. 5 meters, is that sensible? Well, okay, we're going about 10 meters per second, and it's a half a second. Well, okay, I'm going to guess that's reasonable. Is it reasonable for the depth of a lake? 5 meters, 15, 16 feet? Oh, totally. That's totally. If we'd gotten 48 meters, we would know it was wrong. If we got 0.48 meters, that's like this, we'd know it was wrong. So this seems totally reasonable. The sign is good. The answer is good. I think, did we actually answer the question? The question was, how deep is the lake? Ta-da! The lake is just about 5 meters deep, which is a very reasonable answer. So there we go. That's a 2-phase problem. Lots of work, lots of process, but if you just follow the problem-solving process, you will find that you should be able to work your way through the steps reasonably and end up with a good answer. So, good job.